Okay, hello everyone. Discuss contest 8 today. So it was harder than I expected actually. So I didn't expect it to be that difficult, especially problem E. So I obviously misplaced problem F. So problem F should be in position 5. Problem E should be in position 6. But I didn't think it's that difficult actually. Probably too much. Probably too much. It's not that difficult. So no special algorithms needed. No special techniques. Just careful implementation, and that's it. But okay, we'll talk about it. Problem H is actually quite difficult, so I'm surprised two people actually solved it. It requires some advanced, I would say, modular arithmetics. Again, very mathematical problem. So it's not more mathematical than we usually have in this contest. Problem G is quite standard. Problem G is pretty much standard dynamic programming, so probably if you didn't solve problem E during the contest, so Alex solved it, nice. So if you didn't solve it during the contest, I highly recommend to upsolve it because it is very standard. So something like this happens a lot of time. So first problem is pretty straightforward. You just do what you need to do in this problem statement. Again, it's not that trivial, but you just implement simple while loop. So in this while loop, I keep track of how many candles I have and how many burn candles I have. It's went out candles. Okay. So I keep track of how many new candles I have, how many burn candles I have, and just carefully do what need to be done. Constraints are very small, but even if constraints are large, you can do it because like number of iterations is at most log n. Yeah. So every time you burn some candles, then you need to take B out of burned candles to create one new candle. So number of candles is decreased exponentially. So number of steps until you run out of candles will be logarithmic. So this solution is actually logarithmic, but it's not the problem. So if for this constraint you can do it, you can burn candles one by one, it will still work. First implement, you forgot but it compares with left behind. Yeah, that's the yes. So you may kind of collect burn candles from the previous steps. So every time here. So every time I keep track of how many burn candles I have, and every time I add these new candles to this like pile of burned candles. So I keep track how many in total burned candles I have. Yeah. And here also this variable C is specifically for this. Okay, this plus equal should be equal. Okay, I will spend a lot of time figuring out what's going on. Yes, spend a lot of time. Yes, so this plus equal should be equal. Yeah, now it works. So that's basically the full solution of the problem. Maybe it's not even the easiest solution. Maybe you can do it even easier than this, but okay. Either way, pretty simple problem. I hope most of you solved it. So, and some of you did not from the first try. It's actually this one. Yes, that's exactly this problem. Yes. So we need to keep track of how many already burned candles we have. Here we just calculate like this. Okay, it gets wrong answer test 4. Or that may be painful. That may be painful. Okay. Especially in the first problem when you have wrong answer test 4 and you have 3 samples. So it's the first non-sample test, right? Yeah, not the first. Okay, 2 tests here. Okay. Okay, it's possible to spend a lot of time just finding this mistake. Okay, but most of you managed to do it quite fast. Okay, 25 minutes for this problem. Okay, it's kind of painful, but okay, it happens. Okay, but either way, you figure out how to do it. So even if you didn't manage to do it from the first try, you still find the mistake and so on. It's good experience actually. So let's go next problem. Problem 2 is about it's about tournament. It's about two. Okay. So second one is about two. How it's called? Kit for some games. Kit put it kit away from this color. Okay. So we have teams. Each of them have two football kits. Okay, one to play at home, one to play as a guest team, and we need to figure out how many times they play in each of these kits. Pretty straightforward. So all the home games we play in the home kit. That's easy. But some of the away plays we still play in the home kit, and we do it if the color is the same. So the number of times we play away with the home kit is the number of times when our away kit is the same as someone's home kit. Yeah. So let's count for every color how many times this color is someone's home kit, and just take this color, and this is the number of times we play as a guest team but with our home kit. Yeah. And now just simply calculate. So now we play home kit n-1 games at home plus these extra C games, and we play in a guest kit n-1. It's total number of times we play outside, yes, and then minus C, because these C games we play in the home kit. That's pretty much it. I use maps for simplicity. You can actually use arrays if you don't like maps. Okay. In other problem, it maybe make solution a little bit faster. Here it just doesn't matter because all constraints are small, not small enough, so like 10 power 5. So we can use maps. So if we make a linear number of requests to map, it will still fit into time limit. So I just make map for simplicity. So to make the code simple. Yeah. So time complexity is greater now because we use maps instead of normal arrays. You can do it with arrays still. Yeah. Just make array. So okay, map from int to int. So if this first int is small, you can make array, right? But you can use maps as well. Unordered map. Unordered map is slightly faster in C++. Yes. Basically, normal map use some binary search tree inside of it. So it also maintains the order of elements. So it's useful when you care about in which order are elements sorted. Unordered map, like the name suggests, doesn't maintain any order. It's just simple hash map inside, actually. So hash map is usually much faster than tree map. So if hash table is faster than binary search tree. Here it doesn't matter that much. So map is like dict in Python. It's like unordered map is like dict in Python. In Python you don't have ordered sets, as far as I know. Yeah. So normal dict in Python is a hash table. So basically unordered map is the same as dict in Python, as far as I understand how Python works. Do they have ordered set in my? Let's Google. Does Python have ordered? The answer is no. Okay, short answer is no. So you don't have any default data structure which maintain ordered set. Okay, maybe in some special libraries you have some, but normal dict is on unordered, like unordered map. Okay, let's move next. Move next. Problem C. Oh, problem C is actually fun. So what we need to do? So we have basically a tournament tree. Okay, spoilers. Poop, hi. So we have basically a tournament tree. So we have some number of teams here, and we know that in every level the number is even. So basically it tells you that the number is some power of k, or power of 2. Yeah. And we're given 2 teams, and we need to figure out if in which stage of the tournament they may play to each other. For example, if we pick these 2 teams, then they will play in this stage of the tournament. That's it. In terms of tree, you basically need to find lowest common ancestor of these 2 teams. Yes, so you have 2 names, let's say X and Y. So this node is basically LCA of X and Y. So what you can do, you can just build this tree and find LCA of 2 nodes. Definitely will work. Yeah. I did it a little bit easier because I know this tree is perfect binary tree like this. So you can do it much easier. I will just go from level to level. I believe you can do it with some bit magic as well. And just remember which node they both belong to. So I move from these two nodes to these two nodes, from these two nodes to these two nodes, and I just move up until I move to the same node. Yeah, and you can move up just by dividing by 2. So if you enumerate them from 0, 0, 1, 2, 3. Yeah. So when you go one position up, so this is 0, this is 1. The number of the node is just this number divided by 2. So you just go up by dividing the current number by 2. Yeah. And I just move up until I move to the same node. And if I move to the same node, this is the level when we play in the same game. Yeah. So basically, I'm doing simple LCA algorithm. I just do it in a tricky way because I have very special tree. You can do it with normal LCA algorithm as well. So that's it. So again, I do minus so they both 0 indices. Yes. So they started from 0 and now they started from 1. Or start from 1 and now they start from 0. All numbers. And I just move up until they are the same. You see. And also I divide n by 2 to keep track of the final. So if you need to answer final if they meet in the root. Yes, lowest common answer is from LCA. Okay, yes, yeah. Do I have special lecture about LCA? Probably. Okay, I will post it in Discord. I believe I have special lecture about all the trees algorithm, and LCA is like the first of them. But here you don't need it again. It's much easier. So if I reach the root, so number of nodes in the layer is 1, then it is the final. If not, I just output the number of the game. It's just counter I increase here. That's it. That's the whole code. Okay, so you move up like this because you have 1 indices. Yes, because if you have any indices from 1, okay, it's basically the same as a divided by 2 rounded up. Yes, so it's a plus 1 divided by 2. Okay. Okay, so, okay, I agree. If difference is equal to 1, it doesn't mean they play to each other. Yeah, so we need to stop when they play to each other. And it happens, yes, not when difference equals 1, but, okay, so, too hard. Okay, a minus 1 is b minus 1. So let's start from 0. Then they play with each other when a equals b XOR 1. I usually do it like this. And now we don't need this plus here. I believe that's one. Something like this should work. No, I changed this here, so it's wrong as just 1. No, because of this. No, equal should be less priority, no? 1. No, okay. Okay, I'm too stupid today. I can't find a mistake. I'll put 2. While I is not equal. Okay. Okay, now it's perfect. Okay. Okay, that's why I never do online coding in these classes, because I made stupid mistakes and look embarrassed myself. Okay, but again, that's it. Okay. Problem D. Oh, problem C is very easy. So okay, the statement's complicated, but the problem itself is very easy. So basically, what we have in problem D, we have array, and it is guaranteed it is correct. So we need to have, so when you start moving somewhere, so you move somewhere left, somewhere right, and then come. So you will end up with something like here you move to the right, and here you move to the left. So the picture is always like this. Or it may be only left, or it may be only right. So if you have picture like this, you can start, for example, anywhere actually. You can start here, then go right, then go left and finish here. Here you can just start here and move here. Here you can start here and move here. Yeah, so just have these three cases and just solve all of them. Just nothing really interesting here actually. So maybe you can have less cases here. Okay, so that's my solution. So I find the like borders of this segment when I have something written in this from L to R. Yeah, if right one is R, and means they are all equal to R, then I move from here to here. If they all L, I move from here to here. If not, I find this middle point when I have R, 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 and then L, 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 L. Yes, and just do this. Just that's it. Just these three cases. It's very good for them, so they guarantee that the answer always exists, so you don't need to check anything. So no special case. I was thinking what put here, but it doesn't matter what you put here actually. So starting point doesn't matter that much. You can put any point as a starting point. Okay. Okay, now we move to problem E. Okay. Problem E is fun. Okay, so I spend a lot of time just looking at problem statement. Okay, so let's see how I approach this problem. I believe there may be even easier approach than I did. I didn't read the tutorial. So what I did in this problem? So okay, what I basically did, I just simulated the whole process. Yeah, so I simulated all the reflections of this laser beam. How many reflections you can have? No, you reflect on each point of the border at most once. Yeah. So size of the border is small. N and M are up to 100,000. Yeah. So I have 100,000 of reflections from each border. So 400,000 reflections. I can just simulate all of them. Yeah. So what I will do, I will start from the starting point here. Let's see. Let's do it. So you have this. I will start in the starting point 0, 0 in this direction and just go until I feel some border. Then start from here, I go here until I reach another border. Then go here, then go here. So I just make these steps one by one. The only trick is to make each step in one operation. Yeah. So for each starting point in direction, you need to see what will be the finishing point. So I have starting point, let's say x, y, and I have some direction, dx, dy, I usually call it. Yeah. It is direction in which I move. And I know the starting point, I know the direction, I need to find the finish point. Let's x prime, let's say y prime. Yeah. Okay. Looks manageable. So then you need to write some formulas, okay, figure out how to do it carefully, but it looks manageable. Yes. So if you know starting point, no direction, it looks like it's easy to find which point will be the finish. Okay. Now, if we agreed, we can just simulate all this process. Now let's try to solve the problem. So for the problem, we have some what we have indicators. What we have. Sensors. Okay, so we have some sensors. For each sensor, we need to find the first time we reach this sensor. No, let's just do like this. So for every time I move from one point to another point, like here, from here, so here to here, I need to find all the sensors which belong to this line. No, we can remember it. We can remember for each line all the sensors which belong to this line. Okay, Can't we reflect the bore n x times to check which sensor it hits first and the order? Not sure what you're asking. No, number of reflections. So we reflect from each point on the border at most once. So we reflect no more than n plus m times. So number of reflections pretty small. Yeah. So the quick again, the trick is to simulate each this big step in one operation. So you don't move one by one. So you tuk 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 tuk. That will be too small. That will be slow. Yes. Trick is to jump from here to here in one operation, and just find all the sensors you hit when you move from here to here. To find all the sensors, we just need for each diagonal line, find all the sensors belonging to this diagonal line. So I need to find all the sensors which belongs to this diagonal line. No, that's easy again. We have not that many diagonals. Yeah, so we'll just maintain for each diagonal list of all sensors on this diagonal. Each sensor belongs to two diagonals. So if I take this sensor, it belongs to this diagonal up and this diagonal here. Yeah. So I take the sensor, put it in lists for these two diagonals, and then later just use these lists to find all the sensors I hit. That's it. And again, and each sensor I will hit at most 2 times. So it's okay. You can just simulate by hitting every single sensor on your path. Okay, let me just write the code. Okay, what I'm doing here, I just simulate. First, I will simulate the process, and then I will add sensors. Okay, so first I will try to simulate just all the reflections. See that I simulate them correctly, and then I will add sensors and all that stuff. Yeah. Okay, here it should be question mark. Okay, what I'm doing here? Okay, so you start in point xy and move in direction dx dy. Yeah. Here I want to make one step from here to here. Yeah. So I see how much time do I move until I reach the border. No, I do it like this. So if I do in positive direction, I will hit it like this. If I do in negative direction, I will hit it in this time. Yeah. So this tx is time until I hit border x coordinates, left or right border. Yeah. And this ty is the time until I hit one of the borders, top or bottom. Then take minimum of them. Yeah. So that's the minimal time until I hit one of the borders. Yeah. Then I just move. Yeah. Simple. You just take the coordinate and add this vector multiplied by time. Simple vector arithmetics actually. And now I reflect. So I see which border I hit. Okay, so here I break until. Okay, it tells you need to break when you reach one of the corners. But if you reach one of the corners, you then move back and hit the corner 0, 0. So I break when I hit 0, 0 for simplicity. Now I reflect. So if I hit one of the borders left or right, I reflect x coordinate of the vector. If I hit top or bottom border, I reflect y coordinate of the vector. That's it. And again, here I stop actually. See? So I implemented this part, and then I will. Okay, I'm looking what's the problem. I can't understand why I have. Okay. No, not here. Not here. It's funny because C++ thinks your problem is here, but your problem is actually here. Okay. Okay. Here I spent some time to find all mistakes. Do you see the mistake? No? Okay. So t equals 0 for some reason. Okay, I'll just leave you some time to find mistake. Okay, yes, mistake was here, you see. So when you hit the border, your coordinate is not n-1, but n, because coordinates are from 0 to n inclusive. Okay, so that's it. So I check. So this example looks complicated enough. So I look at this example, just see the order of points I hit. Looks correct. Yeah. So I think, okay, I simulated all these steps correctly. So now I just need to add sensors and all these shenanigans. Yeah. So let's add them. So I read all the sensors. Okay, boring model. Okay, I think, okay, I was thinking about using maps as well here, but I decided to use vectors for educational purposes, actually. So every diagonal can be enumerated. Okay, let me show you. How to enumerate the diagonals. Let's say, I have x here and y here. So diagonals like these, you can enumerate by sum x plus y. So in every diagonal, the sum x plus y is the same. Yeah. For this diagonal empty, sum is 0. For this diagonal, sum is 1, 2, 3, and so on. Yeah. So index of the diagonal is just x plus y. Yeah. So you look at the point, look at the sum x plus y, and you know which diagonal it belongs to. If you look at the diagonals, you can enumerate them as like x minus y. So x minus y is the same, but you have negative numbers. So instead of this, I just switch one of the x's, for example, like one of the coordinates of x, and do n minus x instead of x plus y. So I reflect one of the coordinates and use these numbers as coordinates. So again, here I have 0, 1, 2. Oh no, not here. I have 1 here. I swapped x. So this is 0, 1, 2, and so on. So that's how you that's how you enumerate diagonals. So one diagonal will have numbers equal to x plus y, another will be n minus x plus y. That's it. So again, I put this sensor in these two arrays for this diagonal, for this diagonal. Now we need to measure time, so I count how much time do I spend. Okay, now I've array for results. Now I will iterate over all sensors I hit and fill the results for them. What? Why do I have the x? Okay. So I check which diagonal I'm now on. Yeah. So if dx equals dy, I have this type of diagonal. If it is not, I have this type of diagonal. Okay. So now we found out which diagonal we have. I will just iterate over all sensors on this diagonal. Okay, now I figure out I actually forgot to store the coordinates of all the sensors. So I will, okay, so I will remember the coordinates for all the sensors. It's again, iterate for all sensors on this diagonal. Okay, if it's already visited, just continue. If it's not visited, I calculate how much time do I need until I reach this, sensor. So my current point is xy, and point diagonal. So I calculate Manhattan distance. Need to divide it by 2. I will divide it by 2 later because I forgot. Okay, or actually these two parameters are the same. Okay, I can just erase one of them. Okay, it would make the code easier actually. Okay. So I have sum of 2 equal values, and then I will divide it by 2 later. Okay, it's correct. It's just a very strange way to do it. That's it. That's basically the whole. So again, pretty complicated problem. You see the code is pretty long. Let me see how much. Do we have this code here? How much? Again, 60 lines. Not that long actually. We did have problems longer than this, and we will probably have longer problems today even. But it is kind of heavy. So if you didn't have much experience in problems like this, it may be too complicated. But again, no special algorithms needed. no special data structures. I use simple arrays, very simple logic here. So no number theory, nothing actually, just careful simulation, and you try to simulate it effectively. That's it. Okay, let's go to problem F. Problem F is very stupid. I'm not sure, again, it's supposed to be in other position, I believe. So we just have some moments of time. You need to find the, I'll draw it while I print here. Okay. So basically you have, so basically you have some points on the circle. You need to find the maximal distance between 2 points. Yeah, just these points happen to be moments of time. So you need to first move from this format to normal numbers, and then in the end you move from these numbers to the same format. So you need to format time and in both directions. Okay, that's it. So I do it like this. So I put them in array, sort this array, then put the first value in the end again. So I can do this. Yeah, and then just look at difference between 2 consecutive numbers. Here I forgot how to do it in C++. So you need to format time in C++. I always forget to do. There is some function that allows you to do this. I believe you have some printf which will do exactly what you need. But I'm not that good in C++, so I do it like this. So when I'm not sure what to do, I usually not to go to C++ reference materials. I just do it straightforward like this. What my preferred? No, I write all the contents in C++, but usually you don't need to format strings in C++ in competitive programming. So yes, I write all my contents in C++, but I don't know C++ that good. So I know very small subset in C++ which is usable for competitive programming, and normally all these special functions are not that useful. So I just don't remember which one is for which. Okay, that's all. That's it. That's problem F. Very simple. Very simple. I believe who didn't solve problem F? Didn't solve problem F. Come on, it's easy problem. He didn't absolve it. Okay, absolve problem F. It's easy actually. So problem E. Okay, problem E is complicated. I agree, but I still encourage you to absolve problem E. So no rocket science, just careful implementation. J and H, okay, J and H are kind of professional problems. E and F are solvable, especially F. Very easy. Okay, problem G. Problem G is very standard dynamic programming problem. How can you find out this problem is standard dynamic programming problems? Let's look at some hints. So what problem statement hints give us? First of all, you may figure it out. The problem looks like a knapsack problem. Yeah. Now it will open, I think. Maybe. Will it open today? No? Okay, here. First of all, it looks like a knapsack problem. We have very standard knapsack problem. You have some coins. You need to find the sum k. No, at least you need to check if it is possible to get some k. Yeah. Now I think, okay, this is standard knapsack problem, so it must be solved in some knapsack technique. So how we usually solve knapsack problems? With dynamic programming, especially with these constraints. Okay. Now you look at constraints. See number 500. Yeah. So normal knapsack solution will work like a square time complexity. It will be total sum multiplied by number of elements, so nk time complexity. Yeah. Here we have 500, so it kind of suggests you that n cube solution will also fit into time limit. Yeah. So again, just by looking at the type of problem and this constraint, you think, okay, probably I need to write some n cube dynamic programming. Yeah. That's it. So you just do it by just looking at the problem, not thinking about it. Yeah. And now you think about what dynamic programming actually will solve my problem. No. Again, how do you solve problems using dynamic programming? No, you normally do it like this. You kind of want to find a process which will build the object that you're looking for. Yeah. So how this object look like? Well, let's take this example. For example, let's say 5, 6, 1, 10, 12, 2. Yeah. So what I need to do? I need to pick some numbers with sum equal to 18. Let's pick some numbers. 11. Not too much. Okay, do you have something interesting? Let's say 5, 6. Okay, 10 and 2, for example. Yeah. Let's say I pick these 4 numbers, so the sum equal to 18. Okay. How the normal knapsack works? Normal knapsack will go left to right, and for each number you decide you either take this number or skip this number. Yeah, and like you have like position di when you have sum equal to I, and if you take number x, you either take this number and go to di plus x, or you skip this number and go to the same di. Yeah, so that's how normal knapsack works. So you take all your numbers one by one. For each you decide if you take it or you skip it. Yeah? And you remember what is the current sum you have. Yeah? If you take the number, you increase the sum. If you skip the number, you have the same sum. Yeah? Semi-brute force. That's a good question. Dynamic programming looks like brute force, but with memorization. So yes, so you kind of do brute force, but you don't visit the same state multiple times. You can think about dynamic programming like this. So you try all the possibilities, but you kind of form in such a way that you visit each state only once. So normal brute force will go like this. You will go here and then you go here. So if you visit the same here and here, dynamic programming just doesn't visit the same state multiple times. So I will visit here, and then next time I go from here, I just don't go here because I already was here. Yeah? That's how you can think about dynamic programming. For me, it's usually not very useful to think like this, but yes, you can think about dynamic programming like this. Yes, like if I do brute force, but I kind of remember which state I visited, so I don't visit them multiple times. Yes, also valid interpretation of dynamic programming. Okay, so that's how normal knapsack works. I go from left to right. It doesn't matter which orders, like left to right. Yeah. And for each element, I decide if I take it or if I skip it. Okay. Now, what we need to do here? We need from this subset, from this set of numbers, we need to pick some subset. Let's say I pick this element and this element with sum equals 15. Yeah, and that's how I get this 15. Yeah. So I take some numbers with sum 18, and from this set I pick another subset with sum equals 15. Yeah. So how we'll do it? No, we'll do the same. We'll go left to right. For each element, now we have 3 possibilities. We can skip this element completely. Yes. We can take it to the first set and to the second set, or we can take it only to the first set. And I will remember these 2 sums, first sum in I and second sum in J. So now I have 2 parameters. And again, now in position ij, I have 3 possible cases. I can skip this element, so I go to ij if I skip it. I can add it to the first set, but not to the second set, like a plus x and j. Or I could add it to both elements, so I plus x and j plus x. So basically, the same idea, but now I have three possible things what I can do with each number. Again, it sounds easy when you know how the normal knapsack works. So if you didn't solve this problem, probably you don't have much experience with normal knapsack problems. So I will highly recommend to solve more problems about normal knapsack. So after some number of knapsack problems, it just comes naturally. So you look at the problem and think, okay, it's knapsack, but I also have this. And you write normal knapsack, but add some another parameters. Yeah. Every next time it's easier than the... So that's my knapsack. So I will do it like this. I take the numbers. Again, here I go right to left. See, that's how I usually not do knapsack. So you can do knapsack with two-dimensional array, but normally you do knapsack with one-dimensional array. So you just make array D, and from E you wanna update I plus X. Yeah. So you take volume X. So you go from here and update this value. And since you only have one coin, yes, you don't want to have like so you don't want to go here to I plus X and then from here update I plus 2X. Okay, because you can't use the same coin two times, so you can't make this update and then this update. So in my knapsack implementation, I just go from right to left. So I first so this is old value. I update new value here, yes, and then here is old value. I update new value here. So I just update elements right to left. Okay, that's how I usually use one array, but not two arrays. You can do the same with two arrays. Just have old array and new array. How you can do dynamic programming? So you have your old array from previous state, and you have new array d prime. So here is d prime. And you iterate over old array and update values in a new array. So from position I, you update position I here and position I plus X here. Yeah. That's how I normally use dynamic programming. So if it's not some knapsack problem, I would probably do it like this. Yeah. But okay, for knapsack I use simpler implementation. I use the same array. So I just work the same array. So when I do this, I use array D. So when I reach position I, all elements here are already new, and all elements here are old. Yeah. So I update this element. So I update this position and this position, and then move to one position to the right. Okay, just again, it's normal tricks for the knapsack problem. So just make your code much easier, make it slightly faster, but it's not the point. It's the main point is just to make it the code as easy as possible. So that's it. That's the whole code. So this should be J plus X because I'm missing. Yeah. Knapsack is one of the most important problems, actually. Yeah, out of all dynamic programming, knapsack is maybe because it has many different variations. Yeah. No, that's basically whole code. Okay, here it must be J plus X. I make a typo. Think. Okay, looking for the mistake. Found mistake. Yeah, that's it. Okay, so I told you I have three transitions here, but first transition is just stay in place because I have the same array. Yeah, I just keep value dij as it is, so I don't erase it. You see, and then just copy it here and here, and then, just find all the values j which are reachable. Okay, hope it was clear enough. Very professional problem, actually. So if you have a lot of experience in dynamic programming, and especially in knapsack problem, it's no difficulty here. But if it's your first knapsack problem, it's complicated, yes. Or problem H, okay. Problem H is finally some mathematical problem. But it's not hard mathematical problem, actually. So I thought it's much harder when I first read it. It turns out it's not. So first of all, we need to find some probability. And they just tell us that the probability should be some irreducible fraction here. No, how do you calculate probability? How do you calculate probability? You calculate number of total cases and number of good cases. Huh? Yeah. So in my so let me just draw a new problem. So probability is divided. So again, like A divided by B. So A is number of like good outcomes. They call outcomes in probability theory. Okay. And B is total number of outcomes. So let's start from the first part. Let's find what is the total number of different outcomes we can have. No, we have k people, and each of them can have birthday in any of 2 power n days. Yeah. So total number of ways we can assign birthday to all people is 2 power n power k. Favorable outcomes. Okay. I believe I never read probability theory in English. It's fun. So I don't know how the terms sounds in English. Favorable outcomes. Nice. Okay. So so that's total number of outcomes. Yeah. So that's B. So B just equals 2 power n power k. It is actually the same as 2 power n k. Okay. Now we need to find number of outcomes when 2 people have the same birthday. Yeah. How to count? So how to count a number of these outcomes? No, it's much easier to count how many people have how many outcomes when all people have different birthdays. Again, that's some trick you learn a lot. So in combinatorics, so you have so you have some set, let's say, so this is set B, yeah? Inside the set B, we have set A. Sometimes it's much easier to count how many elements are outside. So if you count how many elements are here, then you can count how many elements inside A, just B minus this. Yeah. This is one of the cases. So in this problem, we can do it like this. So here outside of A are outcomes when all people have different birthdays. Yeah. And this is just binomial coefficient. Yeah, binomial coefficient. So A will be 2 power nk minus binomial coefficient. Okay, so I have 2 power n days. I need to choose some k days out of them. Not binomial coefficient, but okay. So order matters, yeah. So number of ways to do it is just 2 power n factorial divided by 2 power n minus k factorial. Let's actually talk this part. So this part is x. Let's look at this part x. How to count it? So if you know nothing about combinatorics, so I can count number of ways I can assign birthdays to people. So all the birthdays are different. So the first person have 2 power n options, which birthday have. Yeah. Second person has 2 power n minus 1 options. Then third one have 2 power n minus 2, and so on. Yeah. The last one has 2 power n minus k plus 1, right? So that's your total number of ways when all people have different birthdays. That's basically it. So I will replace it with x. That's basically two numbers we need to find. Now, small details, small details. First, we need to calculate this number somehow, fast. Second, we need to calculate this number fast. It's not a big problem, actually. So it's just, how it's called? Oh, I forgot. Binary factorization, how it's called? I forgot what is the algorithm. Okay, so you can calculate a number power of some number in logarithm time. Not factorization, it was exponentiation. Yes, like okay. So binary exponentiation, just okay. So we can count this number, we can count this number. How to count this number is it's complicated. Okay. Another complication, it's actually more fun. Second complication, we need to find irreducible fraction. To find irreducible fraction, we need actually find the greatest common divisor of these numbers. That's more fun. Okay, at first, so again, greatest common divisor is definitely some power of 2. 2 power some number. I don't know which variable we need to use. Let's say power d. So we need to find largest power of 2, which divides both a and b. Okay, no, for b it's easy, just nk. Yeah, here also nk. So we only need to find maximal power of 2 which divides x. X looks like this. Okay, so we have two problems. We need to calculate number x, and we need to find maximal power of 2 which divides x. Let's solve the one. How I will calculate x? Okay, now we need to look carefully what we actually need to calculate. And you can see that you actually not to calculate this number, but you need to calculate it modulo some small number. No, come on. So this is strange modulo for this problem. Normally they will use some larger model, yes, like 1,000,000,007, something like this. This pretty small model. So I think, okay, can it help me somehow to calculate this number? And you think, okay, definitely can help me, yes, because okay, so if number of elements is greater than model, so if number of elements here is greater than model, then at least one of them will be divisible by the model. Yeah. So if I have a lot of elements here, the x will be 0. That's that easy, actually. So the code is like this. So if x or if k, so I have k elements here. So if k is greater or equal than modulo, yeah, then it just x equals 0. And else, you just make for loop from 0 to k minus 1 and just calculate this straight ahead. Just brute force calculate this product. Calculate it and take it modulo carefully. Don't have any integer overflow problems. But that's it. That's how we calculate number x modulo a million. Second problem is more fun. So we need to find maximal power of 2 which divides this number. Let's for each number here find the maximal power of 2 which divides this number. Okay, for 2 power n, maximal power of n is n. Yeah. Now for this number will definitely be odd number. Yes, because 2 power n minus 1. So maximal power of 2 is 0. This number will be even number. And it will not be divisible by 4. So maximal power 2 will be 1. See? Okay, and now if you look at all these numbers, if you look at the consecutive numbers and look at the maximal power of 2 which divides them, you will have this sequence. You have 0, 1, 0, 2, 0, 1, 0, 3, 0, 1, 0, 2, 0, 1, and so on. Yeah. So every second element will be divisible by 2. Every fourth element will be divisible by 4. See? Every eighth element will be divisible by 8, and so on. So this normal sequence of maximal power of 2 which divides the number. And you just need to calculate sum of all these numbers. So what I will do, I will count how many numbers here are divisible by 2. How many numbers are divisible by 4? Okay, let me write it like this. So this power d will look like this. It will be n because it's n here. Plus number of numbers here divisible by 2. It's just okay, k minus 1 divided by 2. Floor of this, yeah. Plus number of numbers divisible by 4. It will be k minus 1 divided by 4. And plus and so on. So this is the maximal power of 2 which divides this number. Okay, kind of messy explanation, but I hope you get some ideas. So you try to do it by yourself. It's not that hard actually. So you want to write down this number and see how many factors 2 are in kind of in factorization. Yeah. So you look at each number, think, okay, what is the maximal power of 2 which divides this number? And you get this sequence. And so on. No, not 4, 3. Yeah. Lagrange formula. Okay, I don't know these special terms. Okay, probably have some name. Everybody in math have some name. Yeah. Okay. So that's it. So now again, a lot of so again, this many steps in this solution. You see. So you need to find this step, then you do this step. When you do this step, when you find out when you need to find this step, and then this step. So many steps in this problem, but every step is not that difficult. The problem is that there are a lot of them. So that's why the problem is hard, because you need to do a lot of things, and again to reach this final solution. But we can we actually finished. So what I will do, I will calculate this number, just like this. Yeah. Then find this maximal power of 2, and then just divide by this power of 2. Luckily, you can divide by 2 modulo this, because this modulo is prime, so you can divide by 2. You'll see. Okay, so let's see. Okay, here I think a lot. I think too much. Okay. Okay, I started from the last part. Okay, so this is the last part of calculating this maximal power. So this x is maximal power. Okay, and then I decided why I start from this. Let's start from something simple. So simplest thing is when the answer is 1. Answer is 1 if k is greater or equal than number of days. So I carefully here I check if k is greater or equal number of days. So I don't know what is the easiest way to do it. So I just calculate powers of 2 until I find power of 2 which is greater than k. So I check that the answer is not 1. Yeah. So probability is not 1. Yeah. That number of people is less than number of days. Okay. Okay. Because this case kind of bothered me, because some strange things will happen if you calculate factorials of negative numbers. So not do it. So I just get rid of this case. Now k is less than 2 power n. So I can do normal stuff. Okay, so that's how we calculate b. I decided to do it. I don't want to multiply n by k. So I do it power n and then power k. Because n multiplied by k can be out of 64 bits. So I decided it's easy to do it like this. Still you can multiply n multiplied by k modulo mod minus 1. So powers are also cyclic. So you can calculate this power modulo mod minus 1, but I decided it's easier to do it like this. Yes, this is calculation of this number x. Yeah. Okay. This calculation. Yeah, let's just see. Well, just do it. So I calculate this number. So you need to carefully do it so you don't make any integer overflows here. So I calculate 2 power n modulo, yes, and here calculate this 2 power n minus I calculated modulo, and then everything modulo. So I try to be very careful so that I don't make any integer overflows here. And still in the end, so I have some negative numbers here. So sometimes if you calculate modulo of negative numbers, you have negative number in the end. So in the end, I just do with modulo and check it if negative, make plus mod. Because of how modulo works in C++. I just be extra careful here. And that's it. Okay, so we calculated this. So now we calculate A and B, you see? So this is A, this is B. Already done. Now we just need to calculate this maximal power of 2, which divides both of them. Well, okay, here how you divide by 2. I calculate 2 power mod minus 2. It's basically inverse of 2. Yeah. So instead of dividing by 2, you can multiply by this inverse of 2. And that's it. So that's it. I will calculate this number and just divide both numbers by this. See? Okay, no, I did. I calculate 1 divided by 2 power x and then multiplied by it. Yeah. Yes, now you need to implement binary exponentiation, but okay, that's it. That's the whole code. It's just normal binary exponentiation, nothing interesting here. And surprisingly, it worked from the first try. It not usually happens to me, but surprisingly this time it just worked. So let's read the code once again. So this is special case when number of people is more than number of days. I just get rid of it because it's strange case. Yes, so I do write a separate code which checks this. So I check. So I just multiply by 2, calculate 2 power n. Yes, calculate 2 power n. But I stop when I reach value greater than k. Okay. Okay. If it never happened, then k is greater than everything. Then answer is 1. Answer 1 1. Don't think about case anymore. Now I calculate value of b and a. Just using the formulas I just told you. Yeah? So b is 2 power n power k. A is the same as b minus this coefficient. So I calculate this coefficient. If k is later than mod, then I do this. If k is greater than mod, then this coefficient is 0, so it will not affect the number. As again, you need to calculate number modulo million and 3. Yes. So if your number is greater than million and 3, it will be 0 modulo million and 3. And then in the end, I calculate greatest common divisor like this. So I calculate number of times this 2 divides this number using Lagrange formula like suggested. Okay, in the end, just divide both numerator and denominator by this number in modular arithmetics. So again, many parts of this problem, but like all of them are kind of standard. That's it. Good exercise of modular arithmetics and stuff like this. Let's look at your solutions. Okay, so we have 2 solutions for this problem. Maybe I overcomplicate things. Maybe there is easier solution actually. Okay. Okay, that's the standard, the same modular exponentiation actually. Okay, that's easier check. Okay, so if n is small, okay, I agree, it's easier than what I did. You can just calculate 2 power n. Okay. Okay, okay. So that's the check when number of people is more than number of days. Okay. Okay, that's Lagrange formula, but strangely implemented. Okay. Okay, so this for loop iterates over powers of 2. See? So I multiply by 2 and they look at for all number of powers of 2. And here I just multiply k minus 1 divided by this power of 2. And you need to make plus n to this, no? Why you don't do plus n? Hmm. Hmm. Because here okay, you do power k minus 1. So you already divide by 2 power n. Okay, okay. Makes sense. So you can always divide by 2 power n. So you can just, instead of calculating 2 power n power k, you multiply it, you get 2 power n power k minus 1. Yeah. Okay. Nice, nice. Let's look at yours. That's more like it. That's more like my code. I like the long but clear code. Okay. Find power of 2. Yes. Logarithm k, but it's find logarithm of k. Why? So you make here, you can make for loop. Okay, you can make the same inside this while loop, but okay, why not? Boom. Okay, this again, this is in inversion. So you calculate power modulo 2 is to when you want to divide basically. Boom, 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 boom. Okay, that's the way how you avoid negative numbers in modular arithmetics. Yeah. So you can do modulo mod, then plus mod, so it's not negative, and then again modulo mod in case it's over. That's one of the ways to avoid negative numbers. For me, it's usually easier to write if, but yeah. Good, good, good. So that's it. That was contest 8. Thank you for joining me today. See you next week.